Oh, okay. Looks like we're live. Um, yes. Let me just check that my audio is working. Um, all right, well, hopefully my audio is working. Let's all get started. So welcome to the second half of our sort of Math 2018-2019 workshop. So for those of you who are looking for the first half of the seminar, that was done on I believe Tuesday. So if you're sort of looking for the calculus component and the matrices, a bit of your linear algebra component, that is going to be floating somewhere on our um, oh, audio is good, thank you. That's going to be floating somewhere on our MathSoc YouTube. Um, so if you want to sort of touch up on these topics, feel free to go ahead and watch that. Also, just like a bit of, I guess, housekeeping. I'll be uploading these slides like on our website basically right after the seminar's done. So if you want to sort of have a look at them or use them in your study, they'll be up on the MathSoc website along with all the slides from previous years. So yeah, so today, unfortunately, you guys won't be having the lovely Tim and William who did the first half of the seminar today. It'll be me. I'm also Gerald presenting. And what I'll be covering today is a bit on ODEs. Gerald will be taking over for our Laplace transform, and then I'll be coming back with Fourier series and our PDEs to wrap off. Yeah, so I guess we'll just start off with ODEs now then. I think we're good to go. And if you guys just see like the screen go black for a moment, it's just because I'm checking to see whether the stream um is running all right and just checking for any comments. So yeah, just sort of don't mind that. Oh yeah, oh my, I need to scroll quite a bit, but yeah. Where's my ODEs? Yeah, so that is matrices. I'm just briefly talking about ODEs before we get to that section. Um, these guys are, I would say, quite straightforward. So when it comes to the finals, there doesn't tend to be many questions on ODEs, sort of just one or two. And the questions that you do get, it will just sort of be like one first order ODE, and then like one second order ODE. And usually with that second order ODE, they'll tell you to use like variation of parameters or something. But yeah, so what is a ODE? It's just our differential equations. And just our usual derivatives, not our partial derivatives. So sort of just before I go on to the next page, the main thing that you should sort of do when you see a question, because my next page we have two example questions. The first thing that you sort of want to do with ODE is classify your ODE. And what I mean by classify your ODE is have a look at it and see, oh, is this a separable ODE? Is it a linear ODE? And that's sort of going to sort of inform the method that you use. And of course, it would be really lovely if you guys got like a separable ODE in the finals, but because they're sort of the most straightforward to solve, um, I don't really think we see them too often. And I sort of had to do a bit of digging to find some of these questions. Um, but mostly in the finals, you get a bit more of a tricky looking ODE, and I meant to cover this up earlier. Um, but sort of you might get these sort of tricky looking ODEs, and when you have a look at them, you'll notice that, well, with the first one, it's sort of like it's not linear, right? Because we've got this sort of situation happening here. Um, so, and it's also not separable, right? We can't actually separate all the x's to one side or the y's to one side. And when you sort of get like a situation like this, and for some of you who are looking at this ODE right now, you can probably, see this right here and this right here, and you'll probably think, oh, this probably looks like a substitution question. And this is actually a substitution question. Now, I won't be going through this question today. This is the question that the seminar from, was either last year or the year before, actually went through. And if you want to have a crack at this question, you'll find the work solutions for it still in this set of slides when I upload it onto our MathSoc website. So sort of one for you to have a crack at. The one I will be going through is this example down here, which I took out of the 2018 past paper. And I sort of scribbled this out because, well, I mean, I suppose you guys already saw it. I meant to cover up before I started the stream, but I forgot. But this is also yet another substitution question, because when we have a look at this ODE here, we'll be like, oh, well, it's not separable. It's not linear. And really, anytime you see this y on x, because it's such a common substitution with our ODEs, it's one that you sort of want to get really familiar with. So we sort of might just go ahead and work this one out then. Might go ahead and add a new page on. Okay. So let me just copy the question across. So we've got xy dash is equal to y plus 2x cubed cos squared y on x. And the first thing that we sort of want to do is just prepare this for the substitution, right? Since our substitution is v is equal to y on x, we sort of want to make sure that all our y's look like y on x, not like y, like this y here. So we're just going to divide both sides by x. And what that gives us is something that we can actually substitute really nicely into. And because this sort of question was written for that anyways, it works out really nicely. Okay, so we're ready to substitute into this ODE here now. So let's have a bit of a closer look at our sort of substitution. We sort of want to rearrange this, so we get y is equal to vx. And of course, we're going to need to find an expression for y dash, right? So that's sort of just a bit of an exercise in implicit sort of differentiation. And what we wind up for, okay, sorry, that was a bit of a speech part. What we wind up with for y dash is it's just going to be v plus v dash x, right? So sort of just a bit of product rule and implicit differentiation here. And then we've got everything that we sort of need to do our substitution, right? So we've got y dash here, and we've got our original substitution. So let's just sort of go ahead and do that. You'll get v plus v dash x is equal to v plus 2x squared cos squared v, and we're left with a really nice ODE with just v and x in it. And one other thing that you're going to notice is we've got a v on both sides, and then we can also end up dividing both sides by x. And from then on, this sort of question becomes really easy to solve. We end up with this as our ODE, right? So also dividing both sides by x. And now we can see that this is actually going to be a separable ODE. And we love separable ODEs because all you have to kind of do is just move all the, one variable to one side, the other one to the other side, and integrate both sides. Now, I'm going to, it's so straightforward, I may as well do it. I was going to say I might just skip it, but let's actually do it. So on this side, we're going to have, well, that's going to be sec squared v dv is equal to 2x dx, and of course we're integrating both sides. Just got to write our integral there. And then this side is just going to become tan v, and this will now become x squared, and we cannot forget our sort of constant of integration. Now, the most important thing also when it comes to, substitutions is you're always going to have to reverse the substitution, right? So this v over here is really y on x. So our next step, well, we'll just have y on x is equal to our arctan of x squared plus c, and then final step is just to multiply both sides by x. So that's how you sort of go about doing this ODE. And I think really the most important thing over here with this question is sort of being familiar with, differentiation, implicit differentiation, and sort of, I guess really just watching out for any carelessness going on here. Okay, so that's gonna wrap up our first order ODEs. I think just a few other things also, like I'm not sure if it's really too tested in this course, but like be familiar with linear ODEs using your integrating factor and that sort of approach as well. But yeah, and also yeah. Okay, I've also got this all written out here. Let's sort of move on to second order ODEs. So our second order ODEs in this course, the method that we learn for sort of solving them, in particular, like getting out our particular solution, is variation of parameters. But you should also sort of, I guess the other method is also just guessing the form for our particular solution. Just because variation of parameters can get a bit tedious with, of course, sort of all the integration that happens, and we have to calculate our Wronskian as well. But sort of what the tests kind of look for is just making sure that you're familiar with variation of parameters as well. So sort of let's just jump straight into it. And the first thing you always want to do when solving a second order ODE is you want to find the homogeneous solution. Actually, that's the first step you should always do when you're solving really any non-homogeneous ODE. And what the homogeneous solution basically means is just the solution where this function over here is equal to 0. So we sort of want to start off by solving, well, y double dash plus 9y is equal to 0, and I really should have covered this stuff up. Oh, okay, that's my mistake. But we know when we're solving our second order ODEs, personally I find it quite fun because we're just dealing with a lot of quadratic equations. So of course the characteristic polynomial we get here is lambda squared plus 9 is equal to 0. And the other thing that you sort of have to be familiar with is just the general form that your solution will take on depending on the roots. So we sort of might just recap that now as well. So of course with this question here, since our polynomial is this and our roots end up being complex roots, our solution does take on this form here where we have our cosine and our sine. But just generally speaking, let's say your root was a complex root, but it also had a real component to it. So if you get your roots looking in this form, the solution, the general form of your solution is going to wind up being, you're going to also have an exponential term in it, right? So it'll look something like this, cos bt plus b sine bt. So that's for your complex roots. You also want to keep in mind if you have two roots that are real and different, your general solution is going to be e of at, oh, better not forget that, plus be to bt. And if you end up with, why did I start writing an a? So that's supposed to be a lambda. If you end up with two real roots, like a double root at a, let's say, your homogeneous solution is going to wind up being EAT plus BTEAT. So sort of just this guy here is what you have to watch out for. So that's your general form. But sort of the one we're looking at here, right, is just sort of when we just have a pure imaginary root. Okay, so we've got our homogeneous solution here then. Let's now go on to solving for our particular solution. And the method that we go about using is variation of parameters. So what variation of parameters really is just a big formula. Now, in fact, let me actually just go and have a look at one of your exams right now. I'm pretty sure, like you will be usually given these formulas, but it's sort of still good to kind of remember them. And it's also like not too hard to remember. They're very similar. But basically what we have to do in variation of parameters is we have to calculate these two sort of integrals here. And I sort of highlighted the minus there because you really want to calculate that as part of your integral. That way, when you write your final solution, you don't sort of get confused and miss it. And then also this integral here. And you also want to go and calculate your Wronskian, which is this sort of determinant over here. So sort of as I said earlier, variation of parameters is just a bunch of calculations. Yeah, so let's sort of just jump into the question. And what I might do is right after here, I might add a page. So one thing sort of to point out is what is sort of going on with this formula. And the main thing that I really need to point out is just that pink is not a good color to highlight and then write in red on top of, but let's start. Okay, what I just want to point out is that the yx and the y1x and the y2x that we're dealing with is just the solutions, like a solution given by the homogeneous equation. And that's sort of all it is really, and f of x is this sort of component of the question, right? What I've got highlighted here. So let me also just remember that. So 9 sec 3t. Let's go about and do our calculations then. So first thing we always want to do is calculate our Wronskian. So in this question, let me just delete this page. So in this question, our two homogeneous solutions are going to be our cos over here and our sine over here. So let's just say, well, our y1 of x is equal to cos of 3t. And we sort of don't need to bring that a across here because we only need like just like one particular sort of solution. And like you can chuck a random constant in front of here, but the question is why would you want to do that and make your life harder? So we don't really do that. So we have y1x and then y2 of x over here. And this is sort of just a simple exercise in differentiating and sort of calculating determinant. So our Wronskian is going to be, well, we'll pop cos of 3t up here, sine of 3t here. Derivative of cos of 3t down here, so negative 3 sine 3t and 3 cos 3t. And then we go about calculating our determinant, so that's just going to be 3 cos squared 3t plus, again, because we're minus minus, so we have a plus 3 sine squared 3t. And what we notice is that this is just simply 3. So we have a really nice sort of Wronskian to deal with. Okay, The next component is just a bunch of calculations. So you basically want to, I shouldn't have wrote that mahala earlier. You basically want to compute these two things. This one that I've highlighted just then, that's going to become like a coefficient of our sort of first solution here. And then this guy that I'm highlighting now, we're gonna sort of pop in front of our second solution. So it's really just a bunch of integration, and I'm a bit wary of time right now, so I might just go ahead and pop to this slide here where I've sort of written out the integrals. So I just got this by substituting it into the formula. So if you notice over here, that is just our function over here, and this is the Wronski, and we've got that there. And if you guys just sort of go ahead and do that integration, these are the answers that you should get. So this one's really nice. That sort of just cancels each other out, the cos and the sec over here. And then this one over here becomes like tan. But yeah, so that's the results that you should get. And then if we sort of just plug everything back into our formula, this becomes our general solution. So if we actually have a look at it, I apologize if you guys can hear my dog barking. This is just our homogeneous solution. And then this was our particular solution that we got from our variation of parameters, so we're called YP. Okay. Yeah, so the next section that I'm going into is our forced oscillations and resonance. And the truth is, I'm probably not going to go into this section in too much detail just because I'm a bit wary for time. Most of the seminars that we've run this year have gone quite over time. And the truth is, forced oscillations and resonance is really quite interesting to look at. But in the context of this course, most of the time they will simply just give you like a ODE of this form, and then you go about just solving it like you would solve any sort of other ODE. So sort of what we went through earlier kind of covers off it, because really this is sort of just the equation that we get for it, and all of this m, c, k, f0, omega here, they're just sort of various constants, and we have all the skills to sort of deal with these second order ODEs. But sort of just going through it generally, this might be an example of a question that you get about these sort of forced oscillations. And as you can see, this is sort of just a second order ODE that we can solve. And what I might do, because I have a feeling Laplace transforms is going to take like half an hour, and then I want to focus a bit more on Fourier series and what's the thing called? Oh yeah, partial differential equations. What I might do is sort of just talk through this example quite briefly, and then if we have sort of some time at the end, and if I feel like we need to go through this, we can sort of go through it. But yeah, so let's sort of go about solving this ODE. So as I said last time, first step you always do is you find the homogeneous solution. And this question asks, well, we have this sort of constant c here, and the question asks you to, describe the displacement for, c equals 0, 1, and 2. As opposed to, writing 3 ODEs to solve, it's just easier to solve it with c, like sort of there, and then substitute c in after we've got the sort of solution. So yeah, our characteristic equation is, let me just check you can see that on the stream. Yes, you can. Our characteristic equation is just this guy down here. So again, you sort of just replace all your second derivatives with our lambda squared. First derivatives is just lambda, and our constants is no lambda. And these are the roots you get, and that's sort of just if you just chuck that into the quadratic formula, that's sort of the roots that you should get. And what we can then do is look at the various cases. So when c is equal to 0, 1, and 2. Yeah, so because you'll notice as c sort of changes, the form that our roots takes is also going to change. And as I sort of talked through before, depending on what you get for these lambdas, whether they're, real, whether we've got a double root, whether they're sort of pure imaginary, or like complex, they're going to have a different form for the homogeneous solution. Yeah, so if c is equal to 1, then we're only going to have a single double root, right? Because we have, this component over here is going to be equal to 0. And then our homogeneous solution is going to look like this, which is sort of the form of the solution that I talked through before. And let's sort of have a look at the other cases as well. Well, I suppose the way I structured this question is we also then go and look at the particular solution first, right? And this is sort of what I was talking on earlier about guessing your particular solution. So variation of parameters can get quite tedious, but with some sort of functions that you get on this side here, it's actually quite easy to guess the form of the particular solution. Because our fourth sort of oscillation, like these systems, they always have a function in terms of just sign over here. If I sort of go back to this guy over here, you can see the function over here is just really in terms of sign. You can always use the same guess, really, which is this guy over here. To guess your particular solution. And of course, if you've got like a constant over here, like omega, you want to chuck that there as well. You want to have that in your guess. But yeah, so what happens when you guess your particular solution is then you just go ahead, differentiate it, substitute it back in to the equation, and then do a bit of solving to get your coefficients. A few other things that you can guess, right? Like if your function over here is like ever just a sort of straightforward like polynomial, like let's say it's like t squared, let's say it's even just like like t, some simple polynomial, it's also easy enough to just guess your particular solution to be a polynomial and then differentiate that, substitute it back in to get your answer, as opposed to using something like variation of parameters. Yeah, so what I actually might go ahead and do is if you guys want to actually, let me check the chat. Okay, if you guys want to have a closer solve of the system over here, it's something that I reckon it's a pretty good exercise to actually work through yourself. This question over here, and then we've got all the solutions here. I might pop back to it at the end of the stream if we have time. But yes, for now, I might actually skip down here to our Laplace transforms. And so Gerald will be taking over for Laplace transforms. So I'm just going to check whether he's good to go now. Okay. Okay, let's go.
Hello. Just before we start, can everyone hear me? And if I also drop off a little bit, I apologize. My internet today hasn't been the best. Okay. I'm just going to assume that my audio is good. Okay. So welcome to the topic six. So topic six is all about Laplace transforms. And it's very cool applications to actually various parts of engineering. We're going to look at one particular aspect of Laplace transform and how we can solve ordinary differential equations with Laplace transforms. Okay, cool. So, what are Laplace transforms anyway? So the idea with a Laplace transform is that we have a function in terms of t, so we have a function of time. And what we're going to do is we're going to convert this into a function of space. So the Laplace transform actually transforms a function in terms of t into a new function in terms of s. And what it's going to do, yeah, so and the good news with Laplace transforms is that it is an invertible operation. So at least for most operations or for most functions that you'll see in this course, you have a very nice property that Laplace transforms are indeed invertible. In other words, if we have a function of t, we transform it to a function of s. And if we have a function of s, we have a way to transform it back to a function of t. Um, its definition is a little bit involved. It's so the Laplace transform is an integral from 0 to infinity of f of t times e to the minus s of t with respect to t. So here we're always assuming that t is at least 0. And that's equal to the Laplace transform f of capital F of s. Cool. Okay. Um, so one other function that would be really helpful throughout our journey in the Laplace transform is something called the Heaviside function. The Heaviside step function is, as it suggests, a um, a step function. So it's a discontinuous function, and it's discontinuous. Well, I guess it has an open bracket here. So this is u of t minus a, and this is the value of a. The value at a, so is a bit conflicted. Some people don't define it at all. Some people define it as a half. Other people define it strictly as one of these endpoints. So depending on who you talk to, the Heaviside function evaluated at specific at a um, is debated. I think in this course, we typically use um, u of a to be something like a half or something, or u of 0 to be a half. Um, but of course, this is a debated point. So the first thing we're going to do is to show that the Laplace transform of the step function is equal to e to the minus as divided by s, given this definition here. So I will open up my board. Okay, so we're going to recall the definition of the Heaviside function. So u of t minus a, that's equal to 1 if t is greater than a, and 0 if t is less than a. Okay. And we're going to compute the Laplace transform of u of t of minus a. Okay. So let's just do it by definition. So by definition, this is equal to the integral from 0 to infinity of u of t of minus a multiplied by e to the minus st dt. Okay. Well, let's just break this down by the definition here. So if t is greater than a, then u of t minus a is equal to 1. Otherwise, it's equal to 0. So what we can do here is we can actually break this integral up into two parts, right? So it's equal to integral from 0 to a of 0 plus the integral from a to infinity of u of t of minus. Well, u of t minus a is equal to 1. So in this case, it's just e to the minus st dt. And then we can go ahead and compute each of these parts. So this is 0. This part here, well, that's just going to be e to the minus st divided by s, evaluated from a to infinity. So if I evaluate it at infinity, well, e to the minus infinity goes to 0. On the other hand, if I just evaluate at a, I get that it's equal to, uh, oh, that should be minus here. So this should be plus e to the minus s a divided by s. And that's precisely equal to e to the minus s a divided by s. And that's exactly what we wanted. Cool. So what we've done is we've shown that the Laplace transform of the step function is equal to e to the minus sa divided by s. Okay. And then we have the full working out here as well. So if you needed to refer back to it as well. So let's keep going. So in the second one, we're going to use Leibniz's rule or otherwise to show that the Laplace transform of t times f of t is equal to minus f prime of s, where we define f of s to be the Laplace transform of f of t. I won't do this one on the whiteboard. I'll just kind of go through it, but it's effectively just you apply Leibniz's rule. So you just recall the definition of um, capital F of s. You just look at the Laplace transform of t times f of t, and then use the definition of the Laplace transform to break it down into multiple parts. Right, so we recall the Laplace transform of f of t to be the integral from 0 to infinity of e to the minus st times f of t. So if you just compute both sides, so remember that this is equal to f of s. So if I just take the derivative of the Laplace transform, then I get exactly this. And then from here to the next step, I just apply Leibniz rule. So I push the derivative inside of the integral. This derivative becomes a partial derivative. And then I just compute the derivative with respect to s. And then by definition, I just group this minus t with this f of t to get, well, I can put the minus outside. I get t times f of t. And this is exactly equal to the Laplace transform of t times f of t. So this is really just an application of Leibniz rule, which you would have done in the previous topics as well. And therefore, the Laplace transform of t times f of t is equal to minus the derivative of capital F of s. Cool. Let's keep going. It turns out there are some really nice properties with the Laplace transform. In particular, if I take the Laplace transform of a linear combination of two functions of t, then notice that this is by definition just the integral of a times f of t plus b times g of t. But by the linearity of the integral, I can split this up into two parts, right? So I can split this up into a times f of t times e to the minus st. And then I can also break this up into b times g of t, also multiplied by e to the minus st. So that's equal to this part here. And then that was equal to this part here. And by definition, those are the Laplace transform of f of t and g of t respectively. So if I take the Laplace transform of some function of t plus some other function of t, then I can just split them up, similar to how you can kind of expect this. Well, yeah. So by the linearity of the Laplace transform, you can break them up into two parts. Cool. So pretty straightforward. Um, that's just a really nice property that we will exploit. It also turns out that if I take the inverse Laplace transform, it is also linear as well. Okay, so let's take a look at this problem. So using the table of Laplace transforms, or sort of using well-known Laplace transforms, we want to find the Laplace transform of three functions of t. Okay, so let's do that. Okay. So we want to find the Laplace transform of t plus sine of 2t plus e to the minus t. Okay, so the first thing you want to do is to kind of break this up into three parts, and then you want to compute them sort of separately, right? So let's have a look. So we can break this up into the Laplace transform of t plus maybe plus the Laplace transform of sine of 2t plus the Laplace transform of e to the minus t. Okay, and we're going to compute each of them separately. Well, for the Laplace transform of t, that's pretty straightforward. So the Laplace transform of t, well, by, you know, there's a couple of ways to do it. You can compute this manually, or you can just use your table that you'll be given during the exam as well. That's equal to 1 over s squared. The Laplace transform of sine of 2t. This one is, oh, that's the wrong color. So the Laplace transform of sine of 2t is equal to 2 divided by s squared plus 2 squared. So remember that the Laplace of sine of at is a divided by s squared plus a squared. And so when we have a equal to 2, we obtain exactly what we wanted. And finally, the Laplace transform of e to the minus t. This is equal to 1 over s plus t, plus 1. So in general, the Laplace transform of e to the at is 1 over s minus a. Here, a is equal to minus 1, so we obtain this result here. Cool. And so once you have all three pieces of information, then you can just bring them all together. So the Laplace transform of t plus the Laplace transform of sine of 2t plus the Laplace transform of e to the minus t. Well, that's just the sum of all of these components here. So that's just 1 over s squared plus 2 over s squared plus 4 plus 1 over s plus 1. And then you can just leave it like this. You don't have to simplify it any further as well. Okay. Um, yep, and then we have the solution here as well. So the key here is just to break it up into three components and compute the Laplace transform of each of the components separately. And once you have that, then you get your Laplace transform of the original function. Awesome. Okay, so we're going to have a look at another example where we do use the linearity again. So this one is a little bit more involved, so I think I will kind of step through it a little bit slower as well. So let's go ahead and do that. Okay, so this time we're going to compute the Laplace transform of 5e to the 5t plus 6 minus 4 t e to the 3t. Okay. So again, by the linearity of the Laplace transform, we're going to break this up into two parts. Okay, what I'm going to do is I'm going to bring the 5 out the front, and I'm going to bring the 4 out the front as well. Okay, so now it suffices just to compute the Laplace transform of e to the 5t plus 6 and the Laplace transform of t e to the t e to the 3t. Okay, so we're going to compute each of them separately. So the first thing I'm going to do is to compute the Laplace transform of e to the 5t plus 6. So if I look at this and I try to stare at this a little bit, I don't have a form for this. Um, well, I don't have a way to kind of express this as well-known, um, yeah, so as sort of well-known Laplace transforms. However, what I notice here is that I have a power that is being added together. So instead of looking at this explicitly, let's just sort of rewrite this as a product of two things, and let's see what happens. So this is just a Laplace transform of e to the 6 times e to the 5t. But notice now, this expression here is not a function of t. It's actually a constant, right? So what I can do is I can bring it out the front because the Laplace transform is linear. So that's e to the 6 times the Laplace transform of e to the 5t. And now I have an expression that is of a form that I really want. So this is actually a well-known Laplace transform. This is something that you'll be able to find on your table of Laplace transforms. This is 1 over s minus 5. So in the end, the Laplace transform of this is e to the 6 divided by s minus 5. Okay, so that was fine. Let's have a look. The other one is the Laplace transform of t e to the 3t. Remember that we sort of computed this before, right? Um, what we can do is we can look at uh, the Laplace transform of e to the 3t, and then just take the derivative of that, and then just slap a minus sign at the front. So this is equal to minus the derivative with respect to s of the Laplace transform of e to the 3t, right? This is something that we proved in an earlier exercise. But this is equal to minus, well, if I look at this expression here, this is just 1 over s minus 3. So really, I'm computing the negative derivative of 1 over s minus 3. This has a well-known derivative. You get 1 over s minus 3 all squared. Okay, so bringing this all together, let me just check if there's any comments. Nope. Okay. So bring all of this together, we have now our Laplace transform, right? So our Laplace transform um, of 5e to the 5t plus 6 minus 4te to the 3t. Well, that was equal to 5e to the 6 divided by s minus 5 minus 4 divided by s minus 3 squared. So even though, the function looks pretty scary to begin with, when you sort of break it down using the properties of the Laplace transform, it's not too bad. You sort of want to rewrite a lot of the expressions in a form that you recognize, and can easily look up in a table that you'll most likely be given as well. Okay, cool. And here's the solution if you're interested in the write-up as well. So now that we've sort of had a feel for, Laplace transforms, and we sort of understand how they work and how to use them, we're going to start looking at some theorems and some results that might be helpful whenever we're dealing with harder Laplace transforms, computations at least. So the first one we're going to look at is sort of the Heaviside step function, which we've previously seen. Remember that this is just a step function. Um, there is a cut at A, and we also showed that the Laplace transform of the step function at A is e to the minus as divided by s. Um, this is a really important function because it pops up a lot whenever we're dealing with um, shifts and cuts. So the first shifting theorem we're going to look at, the first theorem we're going to look at is called the first shifting theorem. And the idea behind the first shifting theorem is that, well, if I look at the Laplace transform of e to the minus at, so if I attach e to the minus at onto f of t, then what I can see here is that these two expressions here sort of combine together, and they combine together into this form here. Now, if you look at this a little bit and you stare at this enough, really what's happening is that this is just a transformation on t. This is just transforming t by shifting it along by a. If you make a substitution, you can actually see that indeed you actually get f of s plus a, right? Because if you make the substitution u equal to s plus a, then you get, I guess, yeah. So if you make a substitution here, um, then what you will see here is that you get uh, so here all you're doing is you're replacing s with s plus a. And when you're replacing s with s plus a, that also changes the argument of your function. So in other words, if you just attach a e to the minus at to your function, then you basically just shift it along by a units. And this is exactly what the first shifting theorem says. If you have e to the minus at, then you can compute the Laplace transform of f of t, but then you shift it along by a units, and that's all you really need to do. Okay, so let's have a look at this example. We want to find the Laplace transform of t to the 3 times e to the pi t. Now, if we define the Laplace transform of t to the 3 as f of s, as we usually would, then the first shifting theorem says, well, attaching e to the pi t is really the same as attaching e to the minus pi t. So you're shifting along by minus pi units. And so The first shifting theorem says that the Laplace transform of t to the 3 e to the pi t is really the same as f of s minus pi. And so therefore, all we need to do is to compute this expression f of s. And once we find f of s, then we just shift it back by pi units, and then we get our solution in the end. So it therefore suffices to find the Laplace transform of t to the 3. But if you look at your table, if you look at the table, the Laplace transform of t to the a is a factorial divided by s to the a plus 1. Right? And so you can just substitute a equal to 3, and you obtain the Laplace transform of um, t to the 3. And once you have that, then all you need to do is to shift s by pi units. So here, all we're doing is we're going from the Laplace transform of t to the 3 to Laplace transform of t to the 3 e to the pi t. And to do this, you just shift. So this is your f of s that gets shifted along to f of s minus pi. So every time you see s in the Laplace transform, you replace s with s minus pi to get your final solution. Cool. So fairly straightforward. Um, the first shifting theorem is very powerful because if you have something that looks disgusting, but you have this exponential attached to it, then you can just ignore the exponential. You look at the power that tells you exactly how you want to shift your Laplace transform. So now, given that the Laplace transform of cosine of t equals to s divided by s squared plus 1, this one should be fairly well known. Find the Laplace transform of e to the minus 3t times cosine of t. This is just an application of the first shifting theorem. You see there's an e attached to it. So you go, okay, well, I want to compute the Laplace transform of cosine of t, then shift it along by 3 units. So we have that the Laplace transform of e to the minus at f of t, well, that's equal to f of s plus a. So if I just compute this, then e to the minus 3t times cosine of t, that's just f of s plus 3, where f of s is just the Laplace transform of cosine of t. We're already given the Laplace transform of cosine of t, so we just substitute everything in. We get s plus 3 divided by s plus 3 all squared plus 1. Cool. And here's the written out solution. You can have a look at it in your own time. Okay, so that was the first shifting theorem. It's a fairly straightforward theorem. We're going to have a look at the second shifting theorem now. The second shifting theorem gives us a way to relate the Heaviside function with the expression that we want to compute. So notice that if we apply the Heaviside function, all we're really doing is we're shifting the bounds of the integral, right? So instead of starting at 0, we're starting from a, because anything below a gives us 0. And so if I look at this original integral from 0 to infinity, then it's the same as starting from a, and then we just ignore this Heaviside function. But what I can do here is I can actually make a substitution. Right? Specifically, I can let t be t plus a. And so I obtain this expression, right? And then what I can do is I can split this up into two parts. I can go e to the minus s t times e to the minus as. And then e to the minus as is a constant in terms of t, and therefore I can pull it out of the integral, and then this integral is exactly equal to the Laplace transform of f of t. And so the integral from 0 to infinity of this expression here is actually equal to e to the minus as times the Laplace transform of f of t. But this expression here, this left-hand side, well, that's exactly equal to the Laplace transform of f of t minus a times the Heaviside function um, t minus a. And so the second shifting theorem says that the Laplace transform of f of t minus a times the Heaviside function is equal to e to the minus as times the Laplace transform of f of t. Right? Intuitively, what you can think of is if there is some sort of cut. So if there is some sort of cut at A, then the second shifting theorem would apply. This is especially useful whenever we are looking at the inverse Laplace transform, which we'll cover later on as well. Okay. Okay, so yeah, we're going to look at the inverse Laplace transform. Um, so if we know what capital F of S is, so if we know the resulting Laplace transform, our goal now is to find our original function such that if you apply the Laplace transform, you get f of s. We call f of t the inverse Laplace transform because if you think about what this is saying, okay, well, I wrote it there. We write f of t as the inverse Laplace transform of f of s. And what we want to do is we want to use the first and second shifting theorems to help us simplify our work. Okay. So in Math 2018 and 2019, what you'll typically get given are, expressions where you have this sort of quadratic denominator, and you need to figure out, what sort of method you want to use. So every time you see a quadratic in the denominator, there are sort of two things you want to consider. You want to consider either completing the square or you want to factorize the quadratic, right? Factorizing the quadratic will lead to partial fraction decomposition, whereas completing the square would require you to use the first shifting theorem in most cases, right? Because if you complete the square, you might get something like s plus a squared plus b squared, and then whatever you get at the top, you might get something like either b. Then you know that this is a well-known uh, Laplace transform. You might have s at the start. If you have s in the numerator, then you have another well-known um, Laplace transform. I believe it's something like sine or cosine. Um, and so you'll typically want to use your completing the square method. Cool. So let's have a look at this example and let's sort of walk through how you would go about doing it. So whenever you look at this, you're like, okay, can I factorize this quadratic? Well, if I try to factorize this, I want to find two numbers that multiply to 5 and add to 2. Well, the only numbers that multiply to 5 are 5 and 1 or minus 5 and minus 1. None of them add to 2. So you know that factorizing is not the correct solution. So that's not the method we want to use. So instead, we're going to try to complete the square. So you see s squared plus 2s. Well, that's just the same as s plus 1 all squared plus 1. But to get to this plus 5, you just add 4. And conveniently, this happens to be s plus 1 all squared plus 2 squared. Okay, so let's have a look. So when we complete the square, we obtain this expression here. And notice that if we want to write this as some sort of function that we're familiar with, then ideally what we want is this expression here to be the same as the numerator, right? Because we end up getting s divided by s squared plus a squared, which is a well-known Laplace transform. So what we're going to do is we're going to look at s plus 2 and we're going to decompose it into two parts. we're going to decompose it into an s plus 1 factor. So this is now a pretty familiar Laplace transform. And then we're going to have to somehow deal with this case here. So let's have a look at the first case. So for the first expression, this is of the form s over s squared plus 2 squared. The only difference here is that you have a shift of s plus 1, right? So what we can do is we can look at this as f of s plus 1, where f of s is equal to s divided by s squared plus 2 squared. And this has a well-known Laplace transform. You can look it up in your table, but that's exactly equal to cosine of 2t. Okay. So what we can do then is we can just write f of s, well, that's just the Laplace transform of cosine of 2t. Um, but when we have a shift, we use the first shifting theorem. So we use the first shifting theorem. And with the first shifting theorem, we know that f of s plus 1 was equal to the Laplace transform of e to the minus t times whatever function we had. And so altogether, we get that the inverse Laplace transform of the first part is equal to e to the minus t times cosine of 2t. So this is fairly straightforward. This is just an application of the first shifting theorem. And then we just use the fact that, well, we know what this looks like. Cool. For the second expression, we want to look at this expression here, where we have, well, rewrite it here. So a over s squared plus a squared. Um, and this has a well-known Laplace transform as well. So what we want to do is we want to rewrite our expression so that we get this 2 and 2 business here as well. So to do that, we just multiply by 2 and we just divide by 2. This is exactly equal to the first expression here. But then notice that because the inverse Laplace transform is also linear, we can just pull the half out of the inverse Laplace transform. And then all we're dealing with is this business here. But if we look at what this looks like, well, this is just a Laplace transform of a over s plus 1 all squared plus um, a squared. Um, so we can use both the first or we can use the first shifting theorem. This basically goes to s squared, but we have this e to the minus t business happening outside as well. And then whatever's left over is exactly equal to the inverse Laplace transform. Or the inverse Laplace transform of it will be equal to sine of 2t. So fairly straightforward. So don't be too intimidated by it. You just need to rewrite the expression in a way where the inverse Laplace transform looks like a form that you recognize. Okay, and then we just put everything together, so we get this this that we've already computed, and we get this business that we've also just computed. And if we simplify everything, we can just pull them e to the minus t outside. Okay. So the second method that we're going to look at is actually, well, the partial fraction decomposition. So what we want to do is we want to sort of factor this polynomial, this quadratic, and then we're going to use partial fraction decomposition. So the first thing we're going to do is to notice that we have this e to the minus 2s business happening outside. So what we're going to do is we're going to use the second shifting theorem. And that's going to basically pull this e. This is just basically going to ignore this e to the minus 2s business. So by the second shifting theorem, we know that we get this form here. So we can just rewrite the expression as f of t minus a times, and we have to append this Heaviside function in the end. So in the end, we're going to append this u to the t minus a, but for now, we're just going to compute this f of t minus a. Okay, So we're going to try to find a function f of t such that the Laplace transform of f of t is equal to 7 over ts squared plus 5s minus 3. And in doing so, f of t becomes the inverse Laplace transform of this. Okay, so right off the bat, we can see that it's not too easy to complete the square. You're going to have a lot of um, ugly things happening outside. So maybe completing the square is not the right method we're going to use. Instead, what we're going to do is we're going to try to factor the quadratic. And indeed, if we try to factor this quadratic, we do get a nice expression for we get a nice simplification here. So the next thing we're going to do is to just kind of decompose this into two fractions. Um, and so, however method you want to use to decompose this, you can sort of say, okay, well, everything out, and I just equate the numerator, then I get this expression here, right? I get this expression by just um, equating the numerators. Right, so I multiply a by s plus 3, I multiply b by 2s minus 1, then notice that the denominators become equivalent, and so the way that these two fractions become equivalent is by having the numerators also being equivalent. And that's exactly equal to this expression here. What we can do is we can just group all the s terms together and all of the constant terms together. And then however you want to solve it, you end up getting these two expressions, right? And so what you've done is you've decomposed your fraction into two smaller fractions. Both of them are linear in the denominator, so you can apply your transformations however you want. Okay, so we're going to apply the inverse Laplace transform to both parts separately. So for the first one, we're going to just divide everything by 2. So what we can see here is that you obtain this expression, and this is exactly equal to 1 over s plus a, where a is exactly equal to minus a half. But if you look at this part here, you'll notice that it is actually a well-known inverse Laplace transform. It's exactly equal to e to the minus alpha t, or e to the minus at. So this is actually equal to the Laplace transform of e to the minus a t. And so substituting a into our expression, we get e to the t over 2. Cool. So, the first part, you basically just decompose it into a part where it's easy to compute. For the second part, it's even easier. This is really just a direct application of the inverse Laplace, right? Because we see that um, the Laplace transform of e to the minus at is equal to 1 over s plus a. So if I apply the inverse Laplace on both sides, then e to the minus at is just the inverse Laplace of 1 over s plus a, where a here is 3. And then so you get e to the minus 3t. Putting everything together, we obtain this result here. And so f of t is equal to e to the t over 2 minus e to the minus 3t. But don't forget that our final solution has this Heaviside function attached to it. So you get this expression here. And just remember that in our final solution, we had the shift. We had this shift of, remember there was f of t minus a times u of t minus a. And a is really dependent on this expression here. So our final solution is e to the t minus 2 over 2 minus e to the minus 3 times t minus 2 times the Heaviside function at t minus 2. Cool. Right. So in the last part of the Laplace transform unit, we're just going to look at its application to solving ODEs, which will most likely appear in your final exams. These always seem to appear in your final exams as well. So the key point here, the key behind solving ODEs with the Laplace transform is really these two functions. The Laplace transform of the derivative is times f of s minus the evaluated at 0. And the Laplace transform of the second derivative is s squared times f of s minus s times f of 0 minus the derivative evaluated at 0. If you apply the Laplace transform to your differential equation, you can obtain a result. And then you can just simplify everything in terms of its Laplace transform. Cool. So to kind of get your hands dirty, let's just step through a problem. This would be the last, I believe, the last problem before we go to Fourier series. So the first thing we're going to do, so we're going to we're going to use the Laplace transform method to solve this IBP. So we're given a second order differential equation where the right hand side is a Heaviside function. Okay, so the first thing naturally you want to do is just plug everything in. So the Laplace transform of, so you apply the Laplace transform on both sides, and then you use the linearity of the Laplace transform. Notice that by the previous expression that we had before, this was actually equal to this expression, and then this expression was equal to this expression here. And then what you can do is you can just simplify everything in terms of f of s. So you get that s squared times f of s minus 2. So remember that y of 0 was 1 and y prime of 0 was 2. So just plug everything in. And the right-hand side, well, we computed what that was before. So you basically simplify everything up until this point here. And now all you're really doing is just solving for capital F of s. So f of s is equal to this expression here. And then we're just going to apply the inverse Laplace transform to both sides. Okay. So to do this, the first thing we're going to do is just to compute the inverse Laplace transform of 1 over s minus 2. That's e to the 2t. It's fairly straightforward. The hard part is to compute the inverse Laplace transform of this monstrous expression. The first thing we're going to do is just to take the 8 out, just because it makes things a lot nicer in the end. And then what I'm going to do is I'm going to use the second shifting theorem, right? So the second shifting theorem to kind of bring the e to the minus s out the front. In the end, I'm going to have a u to the t minus a. In this case, it would be u to the t minus 1 in the end. And then that will allow us to simplify this expression to something that we can compute in the end. Okay. So again, what we're going to do is we're going to just perform partial fraction decomposition. We're going to find the solution for a, b, and c such that both sides are equal. You can do this by just equating the numerators. Multiply everything by s times s minus 2 times s plus 2. Equate the numerators, and then you can solve for a, b, and c. You get three equations for three unknowns, so they have a unique solution. And then you can write everything in terms of just linear factors. And once you have everything in terms of linear factors, each of them become easy to compute, right? For the first one, it's just the inverse Laplace transform of 1 over s. For the second one, it's just inverse Laplace of 1 over s minus 2. And the third one is the inverse Laplace transform of 1 over s plus 2. Each of them are well known, so you can just look it up in your table, and then you get your solution in the end. So f of t, in this case here, was minus 2 plus e to the 2t plus e to the minus 2t. And then you just apply the second shifting theorem, and you obtain your final solution. And yeah, and your final solution is just both of the parts added together. And I believe this also concludes the Laplace transform section of the seminar. So I will probably hand it back to Anne to finish off the rest of the seminar.
Oh, okay, yes. Sorry, there was a bit of lag, so I didn't see my stream come up until just then. Okay. Uh, Thank you, Drivell. That was some really good stuff. We all love our Laplace transforms. Well, at least I love our Laplace transforms. I hope you guys do as well. Um, so we're gonna be sort of just wrapping up. Oh no, there's echo. All right, sorry. Let me just mute that. Okay. Well, at least now I know my audio is working. Um, yeah, so I'm just going to be wrapping up with our last two topics now, which are our Fourier series, and also our PDEs, our partial differential equations. Um, so Fourier series. Um, so what Fourier series are, and I actually like the idea of Fourier series is actually really fascinating. Um, But essentially, what they are is we have a lot of sort of situations, not just in engineering, um, but like a lot of the times in engineering, right? Where we have sort of a function that sort of behaves in a very sort of cyclical, periodic behavior. And what that sort of means is that it sort of just repeats itself, right? So sort of, something that's really simple is just sort of like a curve that repeats itself. But it could be, something a lot more complicated than that. So, like something like this, and then that just sort of repeats itself over and over again. And with sort of things that behave in this way, it's sort of hard to, like, for example, write a polynomial or nigh on impossible that sort of describes this sort of behavior. So what we sort of use instead is Fourier series. So where we use our sines and cosines um, to sort of approximate these periodic functions. And that's really nice because sines and cosines are really easy to work with. You can differentiate them easily, you can integrate them easily. And you'll see that, in the next topic, PDEs, we end up using our Fourier series to help us sort of get the solution. Um, so yeah, that's sort of the usefulness behind Fourier series. Um, so on this page here, I just sort of have the formula for our Fourier series, and you guys will be given this, or should be given this, is what I should say, in the test. It's sort of similar, like you'll be given, a table of Laplace transforms, and sort of most of the formulas that you're working with. But these aren't sort of too hard to somewhat memorize as well. Um, and sort of, I won't go through them too strongly, but just something to point out. I feel like a careless mistake is because, like, you kind of remember this as being like 1 on L. Sometimes you forget that for your A0 coefficient, you also have to divide by 2. But yeah, so that's our Fourier series functions. And um, the thing with computing our Fourier series is the hardest part about it, I would say. Actually, I wouldn't say that. One of the annoying parts of computing our Fourier series is we have a lot of sort of integration to do. And the integration can get a bit tricky because what you kind of see here is we have like a product of sort of our function here and this cos term here. And what that typically results in is a bit of integration by parts. And sometimes you might bump into questions where you have to integrate by parts like 2 times. And then you have to do that twice, and then you have to integrate by parts 4 times, and you make a bunch of careless mistakes. But in this sort of course, one of the things that we look at, and sort of one of the things that a lot of the questions focus on is our periodic extensions. And that sort of just reduces the sort of level of computation that we're doing. But I suppose, let me also bring it back. I've gone a bit off tangent. Another thing to keep in mind is our Fourier series are defined for periodic functions, so functions with a period of 2L. But what happens if you don't have a periodic function, right? Then, can we still write a Fourier series representation? And the answer to that is yes, because what we sort of do is we can just extend the function so that it is periodic, and then when we sort of want to analyze it, we'll just sort of look at the sort of domain that we're interested in. So let me just sort of talk about the periodic extensions briefly. So the first sort of type of periodic extension we have is just like our general periodic extension. So I'm going to go in with a really easy example. Let's say I just have a function that is defined as, 1, for, let's say, x between 0 and 1, right? Yeah, let's do something like this. So if I just go ahead and sort of just graph that up. Oh, wait, yes, let's do that. And I might just go ahead and do that in red. So we just have this function over here. And it is, sort of just equal to 1. So this guy isn't periodic, right? But let's say we wanted to do a Fourier series representation of it, then what I can do is extend it so it is periodic. And what I'm going to do is I'm just going to show you an example of a periodic extension. So let's say I just defined it to be 0 as well for 1 to 2, right? So 1, 2. And then what the function is going to look like if I just keep on sort of repeating that pattern, so the period's going to be 2, right? Is I might get and I sort of made a mess of the endpoints here, but let's just sort of put that aside. We might get a function that sort of looks like this, right? And this is a periodic function, right? So it repeats itself. But in the context of sort of Fourier series, this isn't a good periodic extension, and that's because we would still have to go and calculate all sort of these integrals here. And what we really want to be doing is making sure that our extensions are either even or odd extensions. So this that I've drawn here is like a perfectly valid extension, but it's not a good extension. So what I'm going to do is I'm going to get rid of it. And let's talk about our odd and our even extensions. So we've got that. And we've got that. So our function's still going to be the same thing. We're going to just have it going from 0 to 1, and it's just going to be 1. What an odd extension looks like is sort of just, how should I say it? Yeah, so reflecting, you sort of reflect it in this line over here. You basically just want to make your function look odd. So in this case, you'll sort of just take it down here. And then you'll go ahead and repeat that. So over here, it'll be like this, and then it'll be like this. And that's sort of, okay, pretend all the lines are on the same level. They sort of look, something like this. And that's our odd extension. And if we wanted our even extension, I'm going to just copy this over and appropriate it. If we wanted an even extension instead, we're just going to reflect it in our y-axis. So it's actually just going to look like this. That. And you sort of just keep on extending it, so it's actually just a straight line. And the reason we make our extensions odd and even is because, I mean, sort of if you have a look at our sine and cosine curves, our sine curve is a odd curve, and our cosine curve is an even curve, right? So when you have the Fourier series of a odd function, it's going to just be a Fourier sine series. So you don't actually have to go and compute this guy over here, right? Because we don't actually need this cosine term. We only need the sine term over here. And similarly, if your function is a even function, you don't need to go ahead and compute the sine part of it. We're going to have a Fourier cosine series. So you only have to worry about this coefficient over here and this a0 over here as well. Wait. Sorry. Oh, yes. Okay. And yeah, I, for some reason, keep on getting confused between whether cosine and sine is like which one's even and odd, which is a really bad thing to be confused about. That was a mild mind blank just then. So yeah, our even functions are cosine series. Wrong thing. Even is our cosine, and our odd is our sine. And that sort of makes a lot of sense because I don't know why that happened. Because when you actually have a look at our cosine and sine curves, that's sort of what they look like. And the good thing about it is we just reduce the amount of computation that we have to do. And yeah, I think that's sort of the main gist with what we do here. Yeah, okay, so what we're gonna jump into is just a example question. So this was taken out of the, actually, let me just check that everything is going all right. YouTube, okay, perfect. Stream money, okay, yes, okay, perfect. Let's just jump into this example question here, right? So we've got this function f, you know what, I think I can go ahead and show the whole question. Defined on 0 to pi as a half of x, right? So let's just go ahead and sketch that out first. Okay, so let me just copy that across. Wrong thing, wrong color. Okay, f of x is equal to x on 2 for 0 to pi. Okay, and I'm going to not make the same mistake I did last time, which was make a mess of the endpoints. And we want to go from negative 4 pi to 4 pi. Okay. Let's just draw this. Okay. Let's do this. Okay, and let's go ahead and draw in purple. So let's actually just have a sketch of this this function first. So a half of x is just sort of looks something like this, right? And we'll define it there and then open endpoints there. This guy over here is pi. Okay, so this is our function. And what we want to do is we want to do the odd periodic extension, which means we calculate the Fourier sine series, right? So I might also just go ahead and like show you. If we were to calculate the even extension, it's just going to look something like this, right? And then that would sort of repeat. So you'll get like sort of this bunch, this sort of zigzag pattern happening. What we get with an odd extension is we're going to instead sort of reflect over here, right? So now we have this odd looking graph. There we go. And sort of what I'm going to do is at this bottom point, I'm also just going to define it here. So that way it sort of just matches up. And then what we're going to do is we're just going to repeat this to the left and to the right. And that is going to be our graph. So I might just go ahead and draw that up. I don't think I've left enough. Actually, I don't think I've made enough space for this. That. That's just going to be 2 pi, 3 pi. Oh, I kind of have enough space for it. Hopefully you guys sort of get the gist of what's going on there. Undefined. Okay. Basically, I'm sort of not going to waste time drawing it out. So actually, I haven't answered the question. Basically, you want to make sure that your graph actually goes to negative 4 pi and 4 pi on this side. So it's sort of just going to have an extra bit here and then a extra bit up here as well. Okay. So that is the first step of this question. So our odd periodic extension. And the next part of the question asks us to show that the Fourier sine series of f is now this thing over here. And what that means is we only have to go about sort of computing this coefficient over here, Bn, which is sort of given by this formula over here, right? So that sort of saves us from having to do an extra round of integration finding our a coefficients. And the nice thing about this question is we know what our answer is going to be, right? Because the question asks us to, show that the Fourier sine series is this. They actually tend to do this because in the exams, sometimes you'll actually have to use the answers you get here to help you with the next question, which is the PDE question. So they kind of have to make sure that you have the correct solution somehow. So you can actually do the next question properly. So what we actually know is when we calculate our B coefficients, we should actually wind up with this as our answer. And so we can sort of check that we're going correctly. And sort of what I might do. Yeah, so that's sort of what I have written here, right? So all we need to prove is that this, which is just the formula, because our period for this, or our L for this question is just going to be pi. So we get this sort of nice formula, and we have to prove that this integral over here is equal to this value over here. And one of the sort of things to look at is when we're looking at sort of this region from negative pi to pi, our function is actually odd. And we know that our sine is also odd, right? So since f of x is odd, sine is also odd. This whole thing over here is actually going to be even. So what we can actually do, and I don't know whether I should do this by scrolling or writing out. I'll just scroll. What we can actually do is just rewrite this integral over here. So we're sort of just changing these sort of bounds over here. And that actually sort of ends up really nicely because our function is also x on 2, right? So when we substitute that in, we sort of get this as the final interval that we're working with. And if we have a look at this now, all we have to do is one round of integration by parts to get our answer. And one round of integration by parts is always better than 4 rounds of integration by parts. Sorry, I suppose there's a bit of trauma behind those words. But yeah, let's sort of go through that then. And so with integration by parts, this was also a bit low on time because it is 5:41. Still got PDEs to go through. I might just go ahead and sort of show you guys what we have going on here instead of working through it. We're sort of, and this actually might be a integration by parts you guys are familiar with because it's quite a common one. But if you sort of go ahead and integrate that, and I should sort of include this in brackets here, you'll wind up with this guy here as your answer to that integral. But one thing you sort of notice about this is this that I've highlighted here doesn't quite look like what we wanted to show, right? We want to show that it is equal to this thing over here. So how do we actually convert this sort of expression that has our sort of cosine in it to an expression that looks like this? And that's got to do with the fact that when we take the sort of cos of n pi, and again, remember, this is sort of defined for, all your n is equal to 1, 2, 3, and etc. When we sort of consider each one of them, sort of cos of n pi kind of oscillates between being -1 and 1. So for odd n, it's -1. For even n, it's 1. And what that means is we can actually write cos of n pi out like this, right? When n is odd, we're going to get -1. When n is even, we're going to get 1. And this is sort of what we get as the solution. And the nice thing about this is since we are given the answer, we have a bit less thinking to do as well, because we're like, oh, well, we definitely need to get this somehow. And now that sort of works out really nicely. So, yeah, so we've gone ahead and done that question over there. So the next thing we're going to do is our Fourier series questions, like at least this is the 2017 test. I think it's the same for the 2018 test as well. They'll also ask you another question, which is, to what? Sorry, okay, yes. I don't know if I'm missing a word then. I think it's fine. To what does the Fourier sine series of f converge to at x is equal to pi? So, and what this is really going off is talking about the convergence at endpoints for Fourier series. And so what we kind of see is that these periodic extensions can be sort of discontinuous or undefined at the endpoints. And we can kind of see that here, right? We have these discontinuities. But our Fourier series do actually still converge to a value at these points. And that value is simply given by this sort of formula over here. So you're really just taking the midpoint of the left-hand and the right-hand limits at the point. So it's sort of a really nice thing, and I'm pretty sure in this course we don't really go into too much of the proofs and stuff for it. So you sort of just need to be able to know how to compute that. Yeah, I don't think we sort of go too much into the actual, proof of the convergence of that. So yeah, so and actually plotting it out can help you a lot with finding the value, because you can sort of just read it off the graph as well. So let's sort of just go through this question here, right? So to what does the Fourier sine series of f converge to at x is equal to pi? And what we know is since our original was only sort of defined up to pi, our Fourier series actually does end up being what's the word? Discontinuous at pi. And that's like in contrary, like let's say if we did the even extension, it wouldn't actually be discontinuous because you'll sort of just have, oh, wait, yes, you'll sort of just have that zigzag thing happening, right? But in this case, we do actually sort of see that this continuity, and I didn't mean to scroll all the way down there. Okay. So we sort of just calculate the value using this guy over here. So we just go ahead and sort of evaluate it. And where we're getting the pi on 2 from is just, and I also didn't do a good job labeling this graph, since this function, of course, is just x on 2, this point over here is just going to be pi on 2, this point down here is just going to be negative pi on 2. And that's sort of where we're getting those values from. And when you go ahead and actually calculate that, you get 0. And you can see that sort of visually as well, the midpoint of these 2 points here, our sort of left hand and our right hand limits is going to be 0. Yes, okay. So that is our Fourier series. And what we also have with Fourier series is this thing called our Parsifal's identity. Now, our Parsifal's identity is like a really big one, I suppose. That okay. Parsifal's identity is Parsifal's theorem is a pretty, I would say, important one, just generally speaking. But I don't know if I'm not sure whether the test this year is being held on Mobius. So if it is being held on Mobius, I'm like not 100% sure about how they'll get you to do like proof questions. So yeah, but this is sort of I wonder, let me also just check a test right now and see if they give you Parsifals on it. Okay, no Parsifals on the test. But yeah, so what I might do is I might skip over this question for now. Again, it's still going to be on all of the slides, and I think one of the past seminars does actually go through this question in quite a lot of detail. What we might do is I'm gonna start on partial differential equations, and really for any of the questions that is my stream okay? Yes, for any of the questions that I've kind of skipped through, we might come back to them at the end and sort of go through them then. Yeah, okay, so okay. Actually, I'm not quite sure if Parsifal's theorem is going to be covered in too much detail in your finals. Okay, regardless, I might come back to that at the end of the stream. Let's start on PDEs now. So what are our partial differential equations? Well, we did ODEs already, but most of the not most of the time, but we also have our PDEs, which are now our differential equations with partial derivatives. And our PDEs are quite tricky to actually solve. There's a lot of PDEs that you can't actually sort of solve exactly, but you can approximate them using numerical methods. And for those of you who might be studying like 2089 right now, or like in the future, you might sort of work with that in that course, right? For now, in this sort of course, we focus on sort of the PDEs that we can solve without sort of using our numerical methods. And those are sort of our, heat equations and our wave equation. So we have our heat equation, which is just this guy up here. So our derivative with respect to t is equal to, some constant squared times our second derivative with respect to x. And sort of this is the notation that you'll probably see used here and there, just because it's a lot easier to write out compared to this sort of thing over here. It's a lot more readable. And with these sort of questions, what we're dealing with, I wonder if I have some space. What we're kind of dealing with is, let's say we have this bar, and this bar has length L. Then sort of what we're dealing with is we can also have some boundary conditions. So for example, this boundary condition right now is saying that at this point and this point, what's it called? Our temperature is kept at a constant of 0. And then we can also set like an initial condition as well. So basically, these heat equations, we're looking at a bar, and depending on the actual boundary conditions and initial condition that you're given, the sort of physical situation that's actually happening is going to be a bit different. In this case, with these boundary conditions, what we sort of have is, the ends are just held at a constant temperature 0. And some other, I think, common sort of boundary conditions you might see is, something like this. Equals 0, also, or sort of any sort of number here. But yeah, basically we're sort of just looking at the heat flow across this sort of insulated bar. Oh yeah, there it is. There it is. This is the condition that we use when we talk about our insulated heat equation. Basically, what this means is that the heat flow at the ends is going to be 0, right? So we're not going to be losing any heat at the ends. Over time, the heat inside the bar is going to evenly distribute itself. I feel like this is the one that I see a bit more commonly around compared to this guy here. But yes, let's check that the stream is running. All right. Oh yeah, it is on Mobius. Yeah, so I'm not sure how some of the proof questions are gonna work, but yeah, I'm not quite too sure. But we can jump back to particles. I don't know if particles is covered too much in detail compared to some of the other courses where we study sort of Fourier series. Okay, let's talk about the technique that we use to solve our heat equation, or PDEs, sort of like the heat equation. And it's this guy, separation of variables. And separation of variables is really nice. It's kind of like solving a separable ODE, which is sort of which sort of gives away what's going to happen. But basically, when we have a PDE, now let's say we have our variables that we're dealing with are x and y. Those are sort of typically the ones you're dealing with because space and time. What we can just do is assume that the solution has this sort of form. And what that actually allows us to do is when we're sort of breaking up the solution into these two different functions, we don't have to be sort of dealing with two variables at a time then. Essentially the goal is to get some nice ODEs that we can solve, because ODEs are a lot nicer to solve than PDEs, right? So what we're going to just do is assume the function has this form, and then we're going to sort of substitute this into our PDE. That's going to give us two ODEs to solve. And then we can only solve those ODEs when we have a few boundary conditions as well. And then we're going to sort of combine the solutions so that all our sort of conditions are satisfied. And in some of these questions, we're also gonna have to use our Fourier series for it as well. Yeah, so the key is really the substitution here. And in most of the questions, and in all of the questions in this course, PDEs are going to be solved using separation of variables, pretty sure. And you know, we can actually just assume this form works, right? You're not gonna, like, let's say if you were doing PDEs outside of this course, this sort of assumption isn't something that, you can always make. Yeah, so let's talk about it a bit more, and I feel like I shouldn't just try going for here. Let's do that anyways. There's almost always infinitely many solutions to these sort of two ODEs, and what I'm talking about is the two ODEs you get after you substitute this guy up here into your PDE. And what you really want to be finding is the non-trivial solutions. And sometimes in the questions you're given in an exam, you'll be told to like assume something, and then like you'll be able to you'll see when we go through the example. And what we want to sort of take is the superposition of all the non-trivial solutions, and that's sort of what we've actually been doing the whole time. Superposition is just the sum. We've been doing this the whole time, like when we figure out the solution to non-homogeneous equations, we're taking the superposition of the homogeneous solution and the particular solution. Yeah, and of course this is sort of where the Fourier series comes in play as well. And yeah, the exam questions on this section do tend to be quite guided, so I don't think you have to worry sort of too much about sort of remembering the whole process. So I think once you get the hang of it, it's pretty cool as well. Okay, so let's go ahead and solve this question. It's a bit of an outdated question, but I figured I would just keep it that way. That way you guys have all of the more recent sort of exams to practice with. And what we have is our sort of situation is this heat equation over here, and then this very sort of typical boundary condition that we're given. Yeah, so I was planning on solving it generally with just c squared, but I might just go ahead and do it with 4. It doesn't make all too much of a difference. Okay. So let's make a new page here. I'm just going to copy this stuff across. So we have ut is equal to 4uxx, and our initial conditions are ux0 t is equal to ux pi t equals 0, and that's for sort of t. Okay, and I'll just get rid of that. Okay, so these exam questions do tend to be quite guided, so they will tell you like, oh, assume a solution of this form, and then you want to show the certain thing, and that's probably because these questions in total tend to be a bunch of marks. If you mess up on the first step, then it's not the most ideal situation to have, so they do tend to be quite guided. Yeah, so what we can do is we can assume that we can apply our separation of variables. So our solution is going to have this form over here. Let me just make sure my notation is the same. Yes, f of x and then g of t. And then what we're going to do, and this sort of procedure is going to be exactly the same for all of your heat equations that you solve, but you sort of apply another type of equation you might get, which you can use separation of variables on, is the wave equation, which I might just show you right now. Where that bad boy at? Okay, right here. Which is this guy here, where we have also the second derivative of t as opposed to the first derivative with the heat equation. And you'll do sort of a very similar thing with the heat equation and wave equation if you want to use separation of variables to solve it. But in this case, we only need that first derivative here. So, well, we know ut, and because we've sort of split it up, with respect to t, so this f of x is just a constant, right? So when you take that derivative, it's just going to be f of g dash. And likewise, this guy over here, with our g of sort of t is sort of like a constant, I suppose. So we got this guy over here. And what happens if we go ahead and substitute that back into our initial equation, is we get this guy over here, f double dash g. Oh, tiny mistake. Need to add the 4n as well. Whoopsies. Okay, 4n. I don't know why, but my window keeps on moving. Okay. And then all we sort of want to do is we want to kind of do what we do with separable ODEs, and we bring all the f's to one side and all the g's to another side. And I think just by convention, you typically bring that sort of constant, that c squared, along with your g. So what happens is if we just divide both sides by f, we're going to get f double dash on f over here. And if we divide both sides by 4g, we're just going to get g dash on 4g over here. And sort of if we now have a look at this, right? This guy over here is a function entirely in terms of g, right? So it's sort of a function of t. And then this guy over here is entirely in terms of sort of x, right? So what that sort of implies is if this function of t is equivalent to this function of x, then there has to be some constant, which we call our separation constant, we denote lambda, such that sort of what I've written here is true. And that's sort of the whole thing with separation of variables. And I'm pretty sure, like in a exam sitch, let me have a look at this. Yeah, I've also got this written out here. You actually want to go like and say something. Wrong thing I need to highlight. You actually want to go ahead and say something like this. Of course, you're not gonna like be writing in red and blue. But you want to be like, oh well, since left-hand side is a function in terms of x, right-hand side is a function in terms of t only, then we can say that each side is going to be equal to some constant lambda. Okay, and what that then gives us, and if we think about sort of what I was saying earlier, we want to solve some ODEs, right? So the two ODEs that we really get out of it, and let's sort of consider that left-hand side first, is that g dash on 4g is equal to lambda, which is really just this ODE over here, minus 4g dash is equal to 0. Man. Sorry, I just mind blanked for a moment. Yes. It's kind of funny seeing f and g because usually like I use a big X and a big T for this, but it's the same thing. And then the sort of second ODE that we're dealing with is this guy over here, which is really just this ODE over here. Minus lambda f is equal to 0. And I don't like how this guy looks, but that's just me being a bit of a perfectionist. Okay. So these are the sort of ODEs that we're going to be dealing with. And if we have a look at them, these are some really nice and I would say somewhat straightforward ODEs to work with. Yeah, and the main thing is if we actually have a look at these ODEs, we don't like know this value of lambda, right? And depending on whether this lambda is positive, negative, or 0, we're going to have different forms of the homogeneous solution, right? We went through sort of those forms that the homogeneous solution can take on earlier. And the main thing is if you like sorry, let me start that sentence again. And what really actually determines the solution that you get is the boundary condition. So depending on the boundary condition, the form of the homogeneous solution, like which results are trivial and which results are non-trivial, is going to change. Now, at least in this question, they give us this assumption here that like our lambda actually has to be some sort of negative value for us to get those non-trivial solutions. If you aren't given that assumption, then you sort of just have to test all the cases. And when you go about testing those cases, you'll notice at some point, like basically because your solutions are gonna have, A and B in it, like A or something plus B or something. If A and B both become zero, then that's your sort of trivial solution. You sort of disregard that case. But in this question, we actually have the assumption. And I can also go ahead and just check that if K is less than zero, then we will get non-trivial solutions. But it's sort of kind of straightforward. So I'll just take the assumption as is. And what we want to do is use these boundary conditions to show that the possible solutions of f are, is this guy over here, for some constants b of n. Oh my, I have just realized the time is already 6:07. So I'm still gonna sort of keep on going on. It's all right if it runs a bit over time, but I sort of do apologize a bit for that. Yeah, so again, we are solving our sort of first ODE. So the second ODE that I wrote. So we're going to solve this guy here. Okay, so and what we can do is, because we can just assume that our lambda takes on this form over here, minus k squared, and we do that k squared for a good reason, just to make our roots sort of look a bit prettier. But the ODE that we are actually solving is this guy over here, f double dash plus k squared of f is equal to 0, right? And what we know about this, so that's just a characteristic equation as well, it's just this guy over here, right? Is we have imaginary roots to that, right? So the solutions to equations of this form is going to look like this. And I think I might also just go ahead and just verify something right now. Let's actually just confirm that when k is less than 0, our solutions are going to be trivial. And that's because I'm going to go ahead add a page right here. Then I add the page in the right section. Okay, yeah, let's just add it right up there. So again, the ODE that we're working with is f double dash, what was it? Yes. Minus lambda f is equal to 0. So let's actually assume that our lambda is equal to k squared for some k. Have I been saying the wrong thing the whole time? Wait. Yes. Wait. This is a negative lambda. No, not k less than equal to 0. I apologize. I think I was saying some things wrongly for the past few minutes. But basically, I'm going to just take a positive lambda instead. We just want to verify that those solutions are trivial. So again, k is going to be greater than or equal to 0. We're just taking lambda to equal this form. Oh, sorry if that confused you a bit. But basically what happens when we get a ODE of that form is we are going to end up with, let me write this out. So of course our characteristic equation is lambda squared. Oh, that's getting a bit confusing, isn't it? Minus k squared is equal to 0. So our roots are going to be plus minus k. So the main thing we're sort of looking at is when you usually see this, you might be inclined to write your solution. You might be inclined to write your solution using exponentials, because that's sort of what I also mentioned when we went through that ODE section. But the thing with exponentials is that it's kind of, okay, sometimes they're fun to work with. In this case, and just bring, I guess, attention back to the fact that you can also write your answer in terms of your, I'm getting a mind blank on how to pronounce them, but your hyperbolic sort of trig functions, so your coshs and your shines. So the solution that we're actually the form that we're going to be looking at for the solution is actually going to be, sorry, let me see if I actually have it written up. No, I don't. F of x is equal to a cosh of k x plus b sine of kx. So this is actually going to be the form of the general sort of solution, the homogeneous solution you get if you take this assumption instead. And since we are going over time, I might sort of just talk through this briefly, but what you'll notice is if you actually go ahead and substitute those boundary conditions that we have in, again, just a sort of reminder on our boundary conditions, it's these guys over here. What you'll notice when you substitute each one of these in is A is going to come out to be equal to 0, and B is also going to come out to be equal to 0. And the reason we sort of use these hyperbolic trig functions instead is because these guys evaluate more nicely out to sort of 0 and 1 compared to our exponentials. Sort of moving on to that, just in case you guys, I guess, do come across a situation where we're dealing with non-trivial solutions where we have our positive roots, you sort of want to make sure you're writing out your solutions using these hyperbolic functions instead of your exponential functions. Yeah, so moving on, we're going to actually go back to the one we were talking about earlier. And if we go ahead and apply our boundary conditions on, and again, the actual boundary conditions that we had is this one here. Now I might just go ahead and grab that across. I put down the wrong screen, sorry, up here. If we actually go ahead and look at these boundary conditions, essentially what they imply is that the first derivative, like evaluated at 0, is going to be equal to 0, and similarly to that first derivative evaluated at pi. So if we go ahead and actually apply those boundary conditions, yes, sorry. We actually want to go ahead and get sort of this working out here. So I suppose there isn't much for me to actually do if we have it written out here. I might sort of just talk through it. So f dash of 0, we're going to be evaluating this guy here at 0. That's going to give us a is equal to 0. And what we sort of wind up with is this sort of situation here, where if we evaluate sort of that derivative at pi, we get this guy over here, and we know that sine of k pi is equal to 0, or either b is equal to 0, right? So when, okay, I wasn't really clear then. Let me start over again. When we get a sort of situation that looks like this, right? We have two solutions. So either b is equal to 0, but then when b becomes equal to 0, we also have a is equal to 0. So then we have a trivial solution. So we just ignore that part. We can also, I suppose, get the situation where k is equal to 0, that's also an option. But the one that we're going to sort of look at is sine of k pi is equal to 0. And that sort of happens when our k pi is equal to sort of these values over here. So yeah, what that essentially means is that for all our n is equal to 0, 1, and 2, we have this as our sort of general solution. So again, since a is equal to 0, that sort of component of our solution disappears. And we have this as our solution, where our sort of constants b depend on sort of our n. Okay. Hopefully that was all right. I know I messed up some of my little explanation here, but hopefully you guys could follow along with that. Okay. I'm gonna do a quick water break. Okay. That was solving one of the ODEs. We also have to go ahead and solve the sort of first ODE that I wrote up. And this guy over here is sort of a first order ODE, so he's a bit more simple to solve. And sort of what we get, what we get is this sort of equation over here, right? And so what we sort of found out in the previous part is we end up setting k is equal to n, right? So we can actually just write our equation out here like this. And this is a very nice and happy ODE to solve. This is a sort of separable, and we're going to have a exponential solution. And this is what we wind up with. So that's sort of just simply by sort of integrating it. And I feel like generally with this ODE here, you do tend to sort of wind up with this exponential solution. So let me grab a bit more water. And what we do end up with is this exponential solution. Yeah, so that's just the solution to this part of the question here. I'm not sure whether I'm not going to, I suppose, go through the working out of this guy. Yeah. Okay, so what we are going to now look at is the Fourier series part of it. So we mentioned earlier that one of the big sort of applications of Fourier series was in finding like solutions for our PDEs. And in most in most exams, like your question 4, part A is going to be a Fourier series question, where you're asked to sort of find the Fourier series, or you're asked to find the Fourier series. And most of the time, they kind of actually just get you like to prove the Fourier series even, because you kind of need the correct answer to help you out with part B, which is the PDE question that uses the Fourier series. And essentially what happens is if you aren't given an initial condition, so let's say you're given a PDE, you're given the PDE, you're given the boundary conditions, all you're going to be able to obtain is these sort of general solutions for f of x and g of t. But if you are given initial conditions, then you're actually going to be able to find a particular solution. So if you aren't given initial conditions, then we sort of just leave it at this point, right? We can't actually work on further. But in this case, we're going to be given our initial condition, which is that the initial temperature distribution is given by this sort of equation over here, where f of x is this sort of Fourier series over here. Okay, so I might also just work through instead of writing out, just for the sake of sort of reducing time, because I know you guys have exams to study for, so I don't want to spend sort of too long on this. Yeah, so by superposition, basically just adding our solutions together. The general solution that we wind up with is this guy over here, right? So remember, we assumed our solution had this form, right? We assumed that our solution had this form. So that's how we sort of go ahead and we multiply this together. So this was our f of x, and this was sort of our g of t. And of course, we're going to put a little n over there. And so that's the general solution we get. And the initial condition over here implies this. Okay, I feel like this might be a bit sort of tricky to hold on to. Okay, let me think about how I should go about explaining this. So yeah, so we're looking, okay, basically the initial condition, t is set to 0, right? So since our t is set to 0, this exponential part of our general solution is going to disappear, right? So this is sort of our, this that I've highlighted here is sort of this part of the initial condition. And this is going to be equal to f of x. And our f of x here is actually just, we're really just considering that Fourier series expansion. So we said this is equal to that. And if we go ahead and sort of just compare the coefficients, right? So since we have a cosine over here, we're just going to be comparing, the coefficient there. And what we can kind of see is that b of 0, and again, just one thing to, I guess, focus on is the bounds here. So b0 is going to be equal to a half, whilst the sort of general b of n is going to be equal to this whole term over here, right? Because that's the coefficient of cosine. And yeah, so that's sort of what we do. And generally, if we want to go ahead and just write that out, I suppose, then we're just going to replace this guy over here, b of n. You sort of just want to substitute that back in to get your sort of general solution. Right, so you want to substitute those values sort of back in and just write it out. Yeah. Okay, and then final part of the question is what is the equilibrium temperature as t approaches infinity? And what we can sort of write, and this is kind of what I was saying earlier, if you just sort of substitute these values back into this guy up here, what we wind up with is this, right, as our final sort of general solution. And yeah, I guess so just paying attention to those bounds there. And what we want to do is figure out, well, what is our equilibrium temperature going to be as our t approaches infinity? And so what we want to look at is this sort of exponential term over here. And what we notice is as sort of t approaches infinity, and again, oh, sorry, my throat is clogging up. This guy over here approaches 0, right? Because we're dealing with our sort of this sort of exponential curve, right? So as t approaches infinity, this guy's gonna shrink all the way to 0. And what that essentially means is that the sum vanishes. And what we're left with is a half. So it follows that over time, we're going to get the sort of system is going to approach a half. I think that kind of wraps it up. So yeah, so unless otherwise specified, you might have to try all the possibilities for the separation constant when solving ODEs to find non-trivial solutions. It's kind of tedious because you have to like assume that lambda is equal to like k squared, lambda is equal to minus k squared, lambda is equal to like 0, and basically for like one of them, like a and b, sort of your constants are going to come out to be equal to 0, and that's going to be trivial. It's really tedious, and generally, I think in a test they sort of just give you the assumption for the non-trivial solutions. I guess just keeping in mind the tip earlier where if you have not positive roots, if you have real roots, just to write your homogeneous sort of solution, what am I saying? A general solution in terms of your hyperbolic trig functions, that's a good idea. Yes, and often the earlier Fourier series question with all its sort of integration is the most sort of hands-on component of the question. Wave equation. Same sort of shenanigans. Apart from the ODEs are going to look slightly different just because we're dealing with this sort of second derivative here instead of the first derivative. But it's sort of very similar, and you get sort of similar boundary conditions as well. And so with the wave equation, you can use separation of variables again. So you can go through the whole process, assume the form of the solution takes on f of x, g of t. There's also this sort of particular, and I am not going to butcher this bloke's name, solution for our wave equation. And generally what it says is for these sort of arbitrary functions over here, our general solution can actually sort of be written like this. And if you're wondering where this sort of c comes from, the c is just this c squared over here. And so this is like a very like broad equation. It's kind of arbitrary, I suppose. But if we know the initial displacement and velocity, then we actually have a more precise solution. More precise solution to work with, where we actually sort of know what these arbitrary functions are. Yeah, so when it comes to solving the wave equation, yes, you can either go ahead and use this guy over here. I'm sure in a test they'll sort of specify what they're looking for. And the major difference, again, when you use separation of variables is your ODEs are going to look slightly different. So your eigenfunctions are going to be slightly different. And what we have over here is proving this sort of special solution to the wave equation. And this is from the 2017 exam. And surprisingly, this is actually more of a question for the first half of this course, which we covered sort of on Tuesday with our several variable differentiation, and our sort of chain rule. What I am going to do, partially to prevent the seminar from becoming 45 minutes over time, we are going to leave this. Now, I know that sounds kind of bad, because I would suppose that this is one of the sort of harder questions that can pop up in your exam. I would like to think that sort of, solving ODEs, some of the Laplace questions for a series, And like separation of variables is quite straightforward and procedural. Once you get the hang of the procedures, it's like pretty chill. This guy is also kind of quite procedural, but it is one of sort of the harder questions that personally I think when I'm not being very coherent now. Personally, I think it's one of the harder questions that I saw when I was looking through all the past exams, which is why I didn't actually change this question from last time's seminar. And if you guys actually want to have a look at this question in a bit more depth, our previous seminar, now I don't know if we held one, like MathSoc held one for this course last year. I think they did, but it is actually there. But basically, all we have to do with this question is just a sort of bunch of chain rule and sort of algebra there. Again, all these slides will be also posted on the MathSoc website. Like right now, I'm going to do it right now. So if you want to have a look at them there as well, that would be very good. And I guess finally, I'm just gonna wrap it up. Thank you guys for watching and attending, and best of luck with your exams. Um, yeah, so I'm sort of gonna end off the stream here also also just to help my throat do a bit of recovery. I don't think I have it in me to go through this last question over here. But yeah, thank you guys for coming, and good luck with your exams.